So to see how heats of reaction are measured, we need to look at the heat required to raise the temperature of a substance. Okay, so what we're really looking at is how do we measure it? We measure it with temperature. So we need to know the relationship between heat and temperature, since temperature is what we're measuring. And so the heat required to raise the temperature of a substance is called the heat capacity. Okay, heat capacity is defined as the amount of heat required to raise the temperature of the sample of substance 1 degree Celsius. So if you're trying to find out the total heat for the reaction, then you take the heat capacity times the change in temperature. So they multiply by how many degrees the temperature has gone up or down. So Q, heat, equals C delta T. So suppose a piece of iron requires 6.7 joules of heat to raise its temperature by 1 degree Celsius. Then the quantity of heat required to raise the temperature from 25 degrees to 35 degrees would just be 6.7 joules per degree Celsius times the number of degrees Celsius, which in this case is 10 degrees, because we always do final minus initial. So 35 minus 25 is 10, so 67 joules. So it requires 67 joules to heat that iron. Just note that if the temperature was coming down from 35 to 25, delta T would be negative 10, and so the heat would end up being negative 67 joules, and the negative just means that it's being emitted rather than absorbed. Okay, so heat capacities are useful, but not as useful as something called the specific heat capacity, or specific heat, which is actually the heat required to raise the temperature of 1 gram of a substance by 1 degree. So if you had different amounts of the substance, it makes a little more sense to do it this way. So you can see down at the bottom, Q equals SM delta T. S is the specific heat, M is the mass of that compound or that substance, and of course delta T is the change in temperature. All right, so we need to multiply specific heat times the mass times the delta T. All right, so calculate the heat absorbed when the temperature of 15 grams of water is raised from 20 degrees to 50 degrees. The specific heat of water is 4.184 joules per gram degree Celsius. And just note that a lot of times the units are really helpful. And so, you put that you get that specific heat, 4.184 joules per gram degree Celsius. Well, how do you get heat, joules? Well, you're going to have to multiply by grams, and you're going to have to multiply by degrees Celsius. So, that's what the equation tells you to do, but sometimes if you're not sure, the units can often help you figure out where you're going. Okay, so in this case, S is 4.184 joules per gram degree Celsius. Delta T is 30 degrees, 50 minus 20, final minus initial, and it's 15 grams of sample, and so we have to multiply by 15. So the grams cancel, the degrees Celsius cancel, and we get 1.88 times 10 to the third joules, or 1.88 kilojoules. Either way is fine. Here's another example. Large beds of rocks are used in some solar heated homes to store the heat. Assume the specific heat of the rocks is 0.82 joules per gram degree Celsius. So what change in temperature would 50 kilograms of rocks undergo if they emitted 450 kilojoules of heat? All right, so just this is good because just want to be careful with the unit. So Q equals SM delta T. S is 0.82 joules per gram degree Celsius. And just note that your mass is in kilograms and your heat is in kilojoules. So for units to cancel, you need to make sure that they're all in the same unit. So the first thing I would do is convert the kilojoules to joules. 450,000 joules of heat is given off. Convert the 50 kilograms of rocks to 50,000 grams of rocks. I now plug it in. So we're solving for delta T, which is Q over SM. This time, because the heat's being given off, I made that a negative number, 450,000 joules, divided by the specific heat, divided by the mass, and I get a negative 11 degrees Celsius. So in this case, they didn't give you the specific heat or the initial temperature or the final temperature. They just want to know what is the change in temperature. Well, it's an 11-degree change, and it's a decrease. So the initial temperature will be higher than the final temperature. Okay. Just for some comparison, the specific heat of water is 4.18, like we just saw, joules per gram degree Celsius. That is actually a very huge number. It's about 5 times greater than the specific heat of aluminum, which means 5 times more heat is required to heat up a gram of water than 1 gram of aluminum. And the fact that water's specific heat is so high really affects Earth's climate. It keeps the oceans relatively resistant to change in temperatures, and so that's why usually it's a little cooler in the summer. It's a little cooler at the ocean, and it's a little warmer in the winter at the ocean because of this effect of the water. And it's also an important fact for our bodies, and so being able to maintain a constant temperature is a lot of that is due to the fact that specific heat of water is so high. It takes a lot of heat to change our body temperature just by 1 degree. All right, so how can we measure some of these heats of reactions? You may or may not have done it in lab yet, but if you haven't, you will. So a calorimeter is a device used to measure the heat absorbed or evolved during a physical or chemical change. So just keep in mind that the heat absorbed by the calorimeter is the negative of the heat of the reaction. So the reaction takes place in the calorimeter, and you measure. You're actually, what we use is a styrofoam cup with some water in it, and then the reaction takes place in the water, and you're really measuring the change in temperature of the water. And so, yeah, here's a picture of it. So if the reaction takes place, what we're measuring is actually the change in temperature of the water, which is the opposite of what's happening in the reaction. So if the calorimeter perfectly prevents loss or gain of heat, then the heat gained by the solution is the heat produced by the reaction. So again, they're opposite. So if the water heats up, that means the reaction itself was exothermic and let that heat out. So the opposite is true. If the temperature goes down and your calorimeter gets colder, that means that the reaction required heat, and so it took it from the solution or from the water to use in the reaction. So again, the Q that you measure is the opposite in charge of the Q of the reaction. So in an exothermic reaction, you will feel the temperature, well, if you feel it, or your thermometer will notice that the temperature will rise. If you're having an endothermic reaction, then the thermometer will drop because the reaction has to take the heat from the water itself. And so just keep that in mind. All right, so if 23.6 grams of calcium chloride was dissolved in water in a calorimeter, the temperature rose from 25 degrees to 38.7 degrees. If the heat capacity of the solution in the calorimeter, so kind of the whole thing together, is 1,258 joules per degree Celsius, what is the enthalpy change per mole of calcium chloride? So first of all, since it's the heat capacity, joules divided by Celsius, we just have to multiply by the change in temperature to get the total heat of the reaction. So if we calculate that, it's just C times delta T. So it's 1258 times the difference. Let's see, that's 13.7 degrees Celsius. So 17.2 kilojoules of heat was absorbed by the calorimeter, and we measured that as a temperature increase. Okay, so that means that the reaction itself gave off 17.2 kilojoules of heat. So negative 17.2 kilojoules of heat released by the reaction. Now that is for the amount of calcium chloride. So now we have to calculate the heat per mole. We're going to have to figure out how many moles we actually reacted. So calcium chloride has a molecular mass of 111.1 grams per mole. So if we take our 23.6 grams divided by 111.1, we actually reacted 0.212 moles of calcium chloride. So to calculate the heat per mole, we just take the heat that we calculated, negative 17.2 kilojoules per 0.212 mole, which is the same as negative 81.1 kilojoule per mole. So it was an exothermic reaction, and when we measured it, the temperature in our calorimeter rose. Okay, one other thing that we can do with heats of reaction, so many enthalpies of reaction have been measured and tabulated, but there's so many reactions out there, you can't always have the enthalpy for a particular reaction. But it turns out that if you can find reactions with delta H's where you can add together two or more reactions to get the reaction that you're looking for, the delta H's then can be added together in the same way. So let's see, look at bullet 2. If the reaction is carried out in one step or a series of steps, the delta H for the one step is the same as the sum of the delta H's for the series. They should be the same. So the two delta H's are the same. So this is called Hess's law of heat of summation. So for a chemical equation that can be written as the sum of two or more steps, the enthalpy for the overall equation is just the sum of the enthalpy changes for the individual steps. If you haven't done it already, we do a Hess's law lab, and just a quick rundown is we run three different reactions. The first reaction is where we take KOH and we dissolve it in water, and we measure the heat of reaction. And then we take that already dissolved KOH that we did in step 1, and then we react it with hydrochloric acid. So we find a heat of reaction for that reaction, dissolved KOH plus HCl. Then in a third reaction, we take solid KOH that hasn't been dissolved yet, and we immediately react it with HCl. So what's happening in that third case is that you have solid KOH that has to dissolve, first of all, and then the solid KOH reacts with the HCl. And so actually two things are happening all at once. So what we should be able to find is that the delta H for the first reaction, where all we do is dissolve the KOH, plus the delta H for the second reaction, where all we do is react the already dissolved KOH. The sum of those should equal the delta H for the reaction where we do two steps in one. And so that's what Hess's law means. If you can do something in more than one step and you add those together, you should get the same delta H as the reaction done all together. So here's a picture that kind of denotes the same thing. So our reactants are 2 moles of carbon plus 2 moles of oxygen. And what we want to do is get to our products, which is 2 moles of carbon monoxide plus 1 mole of oxygen. Okay, so there's two ways you can do it. You can either go straight, which is number 3 on this graph. So 2 moles carbon plus 2 moles of oxygen give us 2 moles of CO plus 1 mole of oxygen, and delta H is negative 221 kilojoules. Okay, but if we didn't know that and we knew these other two reactions, what if we knew the delta H to go from 2 moles of C to 2 moles of O2 to give us 2 moles of CO2? And then we also knew the delta H to go from CO2 to CO plus 1 mole of O2, so that's step 2. If we add those together, we should get the same as if you did it all in one step, which is 3. So delta H1 plus delta H2 is the same as delta H3. And you get to the same result, it's just whether you do it in one step or 2 steps. All right, so let's actually do an example. Suppose you are given the following data, and you can see those two equations. Could you use these data to obtain the enthalpy change for the following reaction? Okay, so what I like to do when I'm working these problems, obviously what we're going to have to do is manipulate the above reactions to try to get them to look like the bottom reaction, and a few things are hopefully going to cancel out because our bottom reaction doesn't have SO2 in it, for example. But notice that both of the other reactions above have SO2, so hopefully we can rearrange these equations so that they cancel out. What I like to do is just sort of pick one compound that only shows up in one of the two reactions, and then I like to line it up. So for example, the 2s in the reaction that we're trying to achieve is on the left-hand side. Well, if you look at the two reactions I have up on top, the only place S shows up is in the first reaction. It's also on the left-hand side, but there's only one of them. So if I could take that reaction and multiply everything by 2, I'll have 2s on the left-hand side. Okay, then the other thing I'm going to do, and then everything else will have to follow, so I'll have 2s plus 2O2 gives me 2SO2. Now, what happens to the delta H if I double everything? Well, the delta H also doubles. All right, now the other thing I might do is I look, okay, I need to have on the right-hand side. Now the O2 could be kind of confusing because it shows up in both places. So I'm going to kind of wait and see what happens with that. But then now if I look at the 2SO3 on the right-hand side of this equation, I see, oh, in my second equation up on top, I do have 2SO3, but it's on the wrong side. So what if I flipped that reaction, if I flipped the reactants and products to the other side? Then I would have SO2SO3 on the right-hand side. Well, I can do that. What happens to delta H? It just changes its sign. All right, I think it's on the next slide. Okay, so yeah, so see that I took the first equation and I doubled it. So I doubled the delta H. So now it's negative 594 for that reaction. And then I took the second reaction and I just flipped it. So now the 2SO2 plus O2 are on the left and the 2SO3 are on the right. What happens that the sign changes, and so now it's negative 198. Okay, so now if I add those reactions together, see everything on the left-hand side of the arrow, I have 2s plus 2O2 plus 2SO2 plus another O2 are all on the left. And then on the right, I have 2SO2 plus 2SO3. So the 2SO2s can cancel, and then I can add the O2s together to get 3 O2s. And so now I have the reaction that I'm looking for. Well, how do I get the delta H for the final reaction? I have to add together the delta H is for the two reactions that I manipulated. And so the delta H for the overall reaction is the negative 594 plus the negative 198 gives me a negative 792. So remember, if you reverse a reaction, the delta H has to change signs. If you multiply it by a reaction by some factor, the delta H also gets multiplied by that same factor. That's Hess's law. So let's do one more example. Determine the delta H for the decomposition of NaCl according to this reaction, given the following data. Okay, so again, let me focus on the 2NaCl on the left-hand side. According to the equations I was given, I have 1 NaCl on the right-hand side. So I have to flip it, which would make delta H positive, and then I have to double it because I want 2 NaCl. So I need to reverse it and double it. Now what about the top equation? Well, I don't want NO at all, but I do want 1 N2 and 1 O2, and in the equation I'm given I have half and half. So if I double that one and also reverse it, I'll get the N2 and the O2 on the right hand side of the equation. So I have to take the opposite, negative 90.3, and then double it. So alright, so first I reversed them both, and so I reversed the signs, and then I doubled both of them. And so I doubled the delta H's. And then now if you add everything together, notice that the 2NO on the left and the 2NO on the right cancel, and I get the rest of the equation that I'm looking for. And so now if I add the delta H's together, I get the delta H for the overall equation.